La presentación de hoy día va a ser por el PhD Bill Adamson. Es un PhD en Ingeniería de Minas por la Universidad de Western Australian School y es el consultor principal de Adamson para empresas como Codelco, AMSA y BHP. Today we have PhD Bill Adamson. We have studied in the Western Australian School of Mines, and now is the current consultor, the principal consultor of Adamson for companies such as Codelco, AMSA, and BHP. So now, Bill, you can begin with the presentation. And welcome to everybody. And we are the ISEE PUCP student chapter, and we are ISEE located here in Peru. So welcome, and let's begin with the presentation.
Hello, everybody. I'm just sharing the screen now. If you can let me know when you can see the screen.
Yes, Bill.
You can see it now?
Yeah.
Okay. Let me put this into presentation mode. Okay, here we go. Can you tell me, can you see the full screen or can you see the presenter's mode?
We can see the presenter mode.
Okay, I know what to do there now.
Yeah.
How's that? And now?
Yeah, now we can see the presentation.
Okay, excellent. Right, well, Roberto, thank you very much for the introduction, and thank you very much to everybody who's dialed in that has decided to come and listen. I was reviewing some of the people who are here, and I discovered that many of you know a lot more about this than I do. So please raise your hands and offer comments if I say something that could be improved. This is the first of two sessions, and the guys, both from Peru and the ISEE, and also John Watson from the ISEE in the States, suggested that this discussion be put around the concept of blast design for vibration control. And I want to emphasize this is part one, and there will be a part two, and perhaps the guys will talk a little bit about more of that later. So I want to, as the title says, I want to discuss the issue of how we can go about designing blasts to control vibration. And when I say control, I don't just mean lower the vibration. I mean that we could control other aspects of the vibration as well, and to do things with the vibration which are beneficial for different processes within the mining context. So I'll come to that in more detail very shortly. We discussed about whether I could talk in Spanish or in English. The final decision was to opt for English. However, any questions I can certainly answer in Spanish. Some of you know me and are aware of the fact that I can speak Spanish relatively well. Okay, let's get started. So, what I want to talk about today is obviously the design of engineering with a purpose in mind. And that purpose is to optimize all of the processes, or as many processes as we have to optimize, which relate to vibration as an input. One of the reasons that I'm happy to talk in English is that, and it's quite curious, engineer, obviously in Spanish, ingeniero, ingeniera, is a person or is a job title. And that is the same in English. But in addition, engineer is a verb in English, which means it's a doing word. It's something that we can actively do with all the resources that we have at hand to try and produce an outcome, a result, or often a solution, applying a whole range of different tools, some of which I'll discuss during this presentation. And some of them you will see next week presented by Stuart Brashear, which are other kinds of tools. And I'll talk very, very briefly about that during this presentation, but not in much detail. So to the concept of engineering, this rainbow bar, if I could describe it as that, describes pretty much how I see engineering as a chain of different steps. And the steps begin with measuring. Without measurement, we have no data. Without data, we can only guess. We can't really say something sure if we don't have data to work on. We analyze that data as the next step, and hopefully we have enough data and good quality data that we can begin to model that data. And I'll show you an example, a very simple example, as we move forward. The modeling leads us to understand a lot more about that process. And any process that we can understand, usually we can modify. And the modification is so that we can produce a better outcome, or so that we can solve a problem, or to put it another way, so that we can control the process that we're using to do our jobs. One of the interesting tools, one of the simple tools, but very powerful tools that we see everywhere in our industry and many other industries, is the whole concept of PDCA: plan, do, check, and act. And obviously that's the process that we go through in our blasting as well. In fact, in all aspects of our engineering. I took that and I changed it and I made it just a little bit more complex to make it adjust to what I want to talk about now, to what we're interested in. For planning, I describe that as designing, because the whole objective here is engineering design. And I'll come back to more detail shortly. The design then has to be implemented. So that's our version of do. And from then, the same thing applies. We check it. Checking means different things for us in our industry. And we act. We take action. We do something as a result of having carried out our checks. Now, in our case, the plan, the design, is based on, I'm going to see if you can see here we go. Let's see if you can see a pointer. Sorry, excuse me. Pointer, laser. Can you see the pointer now? I guess, I'll assume yes. So our design process happens on the basis of input conditions. No prizes for understanding that. And our input conditions, as we'll talk shortly, have to do with everything associated with the blast, the explosive, the rock, you name it. We make our design on the basis of that input condition. And if we're lucky, we have a very clear idea of our objective. We know exactly, we hope, what we want to achieve with our design. So we take our design and we carry it out. Okay, our design affects obviously the drilling. It also involves the charge. And I want to be very clear that one of the most important aspects of this whole process is charging, but not just the charging as an act, but the explosive that we charge. And I'll make reference to that as we move forward. The charge, the explosive, is fundamentally a most important raw material for blasting. And again, I will go into a bit more detail. When I say time, I'm talking about timing. I'm talking about the things that we do to delay the blasting, to the delays per hole, the delays per row, the sequence of initiation. We have all of that put together in our design. We implement all of this and we blast. While we're implementing, obviously, one of the key things which can sometimes be not ignored, but not done as well as it could be, is the QA/QC of the drilling and the charging. That's critical. Okay, so we'll come to that at some stage as well. We carry out the blast and then we check, but we don't just, obviously in our context, by check, I mean measure. So we will measure everything that we can possibly measure, well, within some degree of reason, both during the blast and also after the blast. So we will look at things like obviously fragmentation, and hopefully we will do that using at least cameras, but hopefully there are a number of systems today which have cameras mounted on shovels, which means that we can get a great deal of high quality data as we dig all the way through the pila, la pila de la voladura. So the blast heap. Sometimes my English actually gets replaced with Spanish. We'll also measure, obviously, the vibration, which is what we're all about today. And we'll also measure things which relate to other aspects of our business, our contribution to the process. We measure potential for damage as we deal with our colleagues, our cousins or brothers and sisters in the geomechanical department. And we'll also hopefully measure the excavation rate. We'll measure how well we've influenced the operations of the shovel and trucks. okay? When we get to act, this is where it gets quite interesting and quite busy. So all of the data that comes from checking, we'll analyze, obviously. And out of that analysis can come two things. I've put the arrows here. They could go in all different ways, the arrows. So as a result of our analysis, we will have results which we can then compare with what we want. So the first thing we do is actually compare the results. Then we can, on the basis of the analysis, we can model. And that allows us to compare different outcomes with, again, with our outcome, sorry, with our task, so to speak. Based on how well we've done here and conclusions that we could have drawn here about how well we've done producing these outputs, we redefine and we come back down here and we redesign. And hopefully we don't have to do that as often as sometimes we do. Obviously, the purpose, or one of the purposes of modeling, is to minimize the number of times that we have to do this redesign. Moving on, just a couple of words briefly. Some of this initial stuff is going to come across as very simple, but the simplicity will get more interesting as we move on. The thing about then controlling blast vibration through design, the first question is, can it be done? Can we do it? And obviously the answer should be yes. Then another question, easy to answer, is why should it be controlled? And what really that means is, what reason should we control it for? What purpose should we control it for? Because as we'll see, there are multiple reasons to control vibration, and those multiple reasons may mean that we have different objectives. Questions we have to ask ourselves, which lead into a process. What does vibration do that's good? What does vibration do for us? What are the things that we wish to achieve? And what does vibration do against us? What are the negative consequences of vibration? Because we have to balance those two things. In order to do that, we have to come up with a conceptual understanding of what creates and controls the vibration. And again, we're talking at a very simple level. What aspects of the blast are going to contribute to the characteristics of our vibration, okay? And then how do we design to actually supply or deliver specific outcomes? And that is probably the main thing that we'd like to take away from today's discussion. So just a quick scan through some of the things that we know vibration does for us, good and bad. Obviously, vibration, first and foremost, delivers fragmentation, but it also delivers damage. And the color coding, you'll figure out very quickly. Green is good, red is bad. So we can get damage at the same time as we get fragmentation. We can also get microcracking. And without getting too complex, I will talk about that subsequently, because there is a good relationship between microcracking and vibration intensity. And microcracking has a number of benefits for the processes that come after blasting, in fact, after production. I put this in blue because it is vibration, but it's not vibration in the ground. I'm talking here about air blast, and I will touch on that shortly. But it is important to stress air blast. It's one of those things that often doesn't get measured because not everybody, not all of the, let's say the legal bodies, the regulation bodies understand that air blast can do far more damage, in fact, than the vibration that travels through the ground. So that's something we need to keep an eye on. When you're talking, as I do a lot at the moment, talk to geomechanical engineers in some of these bigger mines with aggressive pitch slopes and a lot of structure, one of the things that cannot be, should not be allowed, is to allow the vibration to destabilize fractures, large fractures and structures, things like large blocks, things like, let's say, large wedges, large wedge structures, which can actually be destabilized, and I'll discuss that shortly. It requires a different kind of engineering of the vibration. I don't want to talk about this in great detail because I don't actually know any great detail, but what I do know is that vibration is one of the design criteria that is looked at in studies by people like, and forgive me for only naming one company because I only know one company, but companies like Knight Piésold, who would do studies on, you know, the effect of blasting vibrations, but also seismic vibrations, we call it earthquakes and so on. My understanding is that the key vibration parameter for that is actually acceleration. And that's literally all I know about the stability of dams. What we can do is do the engineering to make sure that the acceleration levels are kept as low as possible. And again, one of the things which does actually depend on vibration, but we don't usually consider it as an outcome, is the vibration is used in the design of pre-split designs, pre-split blasts, in order to create these discontinuities, which often are very desirable for the mines. When I come to look at the design inputs that we can control, it turns out that almost every single design input can be traced back to explosive energy, which actually makes sense because, as I've said, the explosive energy really is the raw material for pretty much everything that happens in blasting. As we'll see, in one form or another, it all really comes back to the energy. So obviously the first thing is the quantity of energy and the nature of that energy that we put in the blast hole. In other words, things that are determined by the explosive. And here I'm talking about things that go right back to the basics, the formulations of the explosives, the combination of fuel and nitrates and so on. The sensitization that's used to actually make that explosive tick, so to speak. And then also the product selection, which kind of product do we actually choose to use for different physical circumstances in the mine. The next bit, which is extremely important, and I guess I want to propose a slightly different focus, is the distribution of that energy in 3 dimensions. And that distribution is achieved via literally building roads or building accesses to actually get that energy into the rock mass. And that I'm talking there about the blast holes. So the drilling burden, the drilling spacing, it determines basically the whole network of means in which we can actually expose the rock to explosives, or the other way around, the diameter of the blast hole, the depth of the blast hole. The word I like to use talking about energy is to describe it as flux. The same way you could have, electromagnetic flux. So we're creating basically an amount, a presence of this energy distributed through the rock mass. And again, design is all about that. The release rate, in other words, how quickly is the explosive energy actually unleashed and delivered to the rock mass. And that has a lot to do, again, with priming, which I'll only mention now. I won't talk about that again. When I say priming, I'm talking about boosters, obviously, but also the selection of delays, retardos between charges in the same row and between rows for different reasons, and the technology selection. When I say technology selection, obviously I'm talking about the ability to choose between pyrotechnic, shock tube delays, and what is very common these days, the electronic initiation technology. The release or the liberation, and I describe this as vector selection. And what I mean by that is, again, the initiation sequence, which will determine the direction in which we either amplify the vibration on a macro scale, or maybe attenuate the vibration. It also has a lot to do with how we will induce the rock mass to move. And that has a lot to do with damage. Not so much to do with vibration, but the same things we do to design for vibration will have an impact on the displacement of the muck pile. Containment is very, very important. We spend sometimes quite a lot of money to obtain this explosive. We spend some considerable money in getting that explosive into the hole. And if we're worried about fragmentation, it's not a good idea to not have good stemming and just let all that energy fly out again into the atmosphere, causing problems with noise, causing problems with dust, and sometimes contributing to some problems with small fly work. So stemming is actually very crucial and often underestimated. The other possibility, of course, is that we want to use just a bit of the budget of energy that we put into that hole, in which case we go the other way. We might take out all the stemming, we might have a small amount of stemming and a substantially long air deck within the hole. But all of these things have to do with choice about how we wish the explosive to cause our vibration. The other thing, obviously, is what I've called the impact modification. And I'm simply talking there about decoupling the charge from the rock. So for example, like pre-split creation and the sort of decoupling that we do to produce more effective buffer charges, which break the rock just so, but don't do too much damage. And there may be others. I ran out of slides, so I didn't even think about others. So a case for vibration measurement and control, we have to think about the reason. Why do we want to control the vibration? And what I want to show quickly now, or relatively quickly now, is a kind of case, something there where the outcome is very clear to us, and it will become very clear what I am talking about very shortly. When an external person or regulatory body or some other authority actually imposes the condition, the outcome on us, that can be a positive thing, because then we don't have to worry about imagining what we might have to do to keep the customer happy. The thing that has to be done to keep the customer happy is told to us. The objective is very clear. The objective is absolutely quantified, and it's understood by everybody. And obviously the example I'm speaking about here is compliance. Compliance, mostly in a, let's say, an environmental context, where we have to make sure that our blasting results do not go above these typical lines. This is the DIN standard, and over here we have the US Bureau of Mines standard. And we have strict limits that theoretically we must not exceed. Sometimes we do. It's usually a statistical number of blasts fired where we are allowed to exceed these limits. I'll also talk about this later, the fact that as the frequency of the vibration, which is something else we can design for, if the frequency is higher, we are allowed to generate higher levels of vibration. And I'll explain at least one version of why that is so. Sorry. Here we go. Sorry, and I wanted to replace the word measurement and so on with engineering, because I want to come back to that again and again and again. Engineering is something we do, and something we do that affects every outcome that we could possibly imagine. Here's the background to this concept. Not all the countries, but many countries in Europe, the States, Australia, in Chile, in some places, Peru for sure, absolutely. The operations that involve drilling and blasting have to measure, have to monitor vibration levels that are produced at either the lease boundary, where the mining property stops, or somewhere outside the property, but where the public is being affected by what we do. It might be a village, it could be a church, it could be a pipeline. There's any number of things that do not sit on the mine land, but we will cause an effect on, and we have to keep those under control. It's usually far field. It's inexpensive in the grand scheme of things. We have the ability to get seismographs, which are easy to use. They're designed for this purpose, and they're not tremendously expensive. In some cases, the mine people, the mine engineering staff, must do this measurement and this analysis. That's my understanding from working with some quarries and mines in the States. Excuse me. When that's not so, and I suspect that's for legal reasons. However, when that's not the case, it can be done by contractors, consultants, explosive suppliers, and so on. This is all done to demonstrate the compliance with those regulations. It also helps us to understand how the vibration relates to the blast design. And that can be by virtue of growing experience, by simply being there for a long time and trying different things, but always measuring what happens. Or it can be through blast design and implementation with measurement and so on, with modification. This is usually done, obviously, at critical locations. Staying in compliance, obviously, compliance means obviously making sure that we comply with the level that is allowed to do. In some places, we're lucky enough to have standards. In the US and Canada, I believe, certainly the US, there are standards which are recommended. The ISEE has a very good complete standard and recommendation for things like types of geophones, coupling, and what have you. So those things are key. We have to make sure we do these properly. The geophone has to have certain characteristics. based on what we're trying to measure and where we're trying to measure it. There are suggestions about the signal acquisition. I won't go into this at this point in time. It'll be maybe for another day. But I mean the sampling rate, how quickly we sample and so on. And then there is the type of signal analysis which has to be done as a minimum. Many of the seismograph technology sources will have built-in algorithms or built-in abilities to actually print out a report which automatically complies with all of the required standards. So that's obviously is a big help. It's very simple engineering at that point in time, and often we would like more. Personally, I would like access to the raw data that was put into the graphs, because we'd like to do further analysis using that information. And the suppliers of those instruments are usually very good about making that data available. We have to then obviously demonstrate that our levels of measuring comply with these standards, and there are other standards, of course. Spain has a very comprehensive standard. One thing that is very, very important, and it's something that I often drive people crazy with, is the issue of geophone mounting. The bottom line is that sensor, whether it's a geophone or an accelerometer, should feel like it's part of the same rock. That's the basic objective. So wherever the rock moves, the sensor will move exactly the same. That is really never actually fully achieved. But it does depend on the quality of the mount. And just, I guess, a piece of information that is an incentive to do it right is that the typical old trick of putting the geophone on the ground and throwing a sack of rock or a sack of gravel on top of it, a sandbag, will actually deliver a higher reading. The lowest reading you're likely to get from a geophone is going to be when it's correctly coupled. So if you're on the edge of compliance, it really is worthwhile doing a bit more work on that. And if we're out of compliance, obviously we have to find options. We have to engineer change. We could change the size of the blast. That can be a real problem, at a big impact on productivity in mines. The site of the blast, very difficult. I mean, really, if you chose to blast somewhere else, you're messing with the mine plan, and it's really only postponing the problem. Here we start to get interesting. You could, and we do, vary the direction of the initiation of the blast. We may have exactly the same blast design in terms of holes, burden, spacing, but we change the direction of initiation, and that can help us a great deal. Or we can modify the design parameters up front. We can modify the explosive type. We can go for less powerful explosives if we can deal with less fragmentation. We can alter sometimes the blast hole diameter. We can make changes to the stemming. And as I said, we can really control the timing selection. Your timing control is the fine tuning on your blast for pretty much every kind of engineering thing. How big is this change going to be? Is it that we're going to have to put in place? And when I say big, I mean effort. And when I say effort, I mean cost. How much is it going to cost for us to stay in compliance? And maybe there are different ways to do it. And then we want to go for the one that's maybe easiest to apply and also the lowest cost. But at the end of the day, compliance is very straightforward. If you don't comply, after a while, they'll close you down. They will close your operation, and then the whole economic question becomes irrelevant. Measuring and modeling with a purpose, just quickly. We need to know what's going to happen if we make changes, okay? We need to have the ability to predict the vibration based on these changes with some degree of confidence, okay? Now we can measure blast vibration, and we can measure it well, which means that we have a good chance of developing a cause and effect model with which, or in which, we can have confidence. Now, confidence in predictions of the model relate directly to the quantity and the quality of the information and the data that we're going to work with. If we have a reliable model and it's properly calibrated, we have the ability to seek out the compliance, establish the compliance, while maintaining efficient mining. In other words, we have some leg room in which to move. Now, these predictive models can look very different. They can be very complex. They can be quite simple. But in reality, we should start with something simple. And I think pretty much everybody has seen this concept. I'm talking about the very simple scale distance model. Okay, we need, as I said before, we need to know what's going to happen if we make changes. This model can give us at least the beginning of understanding what will happen to the vibration when we make choices about changing. It's all about the capability of relating what we measure to what we did, or the other way around, how we have blasted. And this scale distance model, the equations are there in front of you, very straightforward. The key thing here, obviously, is that K and alpha are parameters of the model, which come from fitting field data. D is simply the distance between explosive charge and the measured point. That can actually be complex. And the mass of explosive, shown as W, is the mass which is contributing to the vibration. And again, sounds simple, can be complex. We'll touch that very briefly. Essentially, what we need to do is collect a lot of data and relate that data to what we measure, okay? That has to be done, or that is done, by measuring a substantial amount of data, the more the better, and we plot trends which allow us to literally calibrate an equation, which you've seen there. The input, if we know the number of kilos of explosive or pounds at a specific number of meters or yards, which will provoke a measured amount of vibration, whether it's millimeters a second or inches per second. And these numbers are plotted as we see here. This is basically a synthetic case. So what I'm showing here is a plot of the model with field data plotted onto that model to establish if there is a trend and what that trend is. And simplistically, this number, this intercept, has a lot to do with the source origin. In other words, the energy which is being detonated at any given place. Now, the issue here is this line is an average. And as you'd know, for compliance, an average is no good per se, because an average means that half the time we will be out of compliance and half the time we'll be okay. So we need to establish a higher value of K, which will give us a degree of confidence. And typically we might talk about a value of K, which gives us a 95 confidence of compliance. But as you can see, because our data is scattered, that K number has to be quite big. In other words, the difference between the average and the acceptable standard has to be quite large, which means that we have less room to move because our predictions could indicate that we are always going to have quite a high risk of non-compliance. So we need to do something to increase our confidence. And that comes from the quality and the quantity of the data that we collect. Okay. Also, and this is very critical, the accurate recording of all the blast hole locations and the amount of explosive in each. Again, we're talking about QA/QC. The more vital this compliance is, the more we should be happy about doing all this work. We also need to know about the timing sequence for the design, which is usually straightforward, and a confident estimation of the vibration levels, which are going to be expected at whichever source of initiation. In other words, for any size of blast hole and explosive selection fired at a known distance from what I've called the point of interest. In other words, where we are concerned about the vibration. And this ability commences the process, our engineering process, to optimize the blast design. But, and again, you'll see this many times, quality counts. The quality of what we do is important. It makes life easy for us. And I'm going to read this because it's very straightforward. The more accurate we know, which means the more accurate we've recorded the charge weight in each hole, the better the fit of our model. The more accurately we have the location of each charge, the place, and that of the geophone, the better the fit of our model. The more rigorous, the more attention we pay to collecting the vibration data, including mounting and so on, the selection of the correct sensor and so on, the better, again, the fit of our model parameters. And the better the fit of our model parameters, the more we will be able to trust our predictions. And that means we can be less conservative with what we do with our engineering. We may be able to use more explosive. We may be able to blast larger blasts. The bottom line is our data now begins to look something like this, where the same trend is in evidence, but the amount that we have to increase the K factor by is less. And what that means is that we can make bigger changes to our blast. blast design, because we have more confidence about where that blast design is going to put us on this graph. Back to quality again. You'll notice that there was a lot less scatter and uncertainty on that synthetic plot. That means we have more confidence in the predictions. It means that, as I said before, we don't have to play with too much uncertainty with K. And it also means we can then take, as I said, a more adventurous approach to the design so that we can, for example, get better fragmentation, maybe more efficiency from our fleet, a bigger fleet, and also maybe other efficiencies such as larger blasts. It turns out that firing larger blasts has an enormous effect on the productivity of the mine on a grand scale. So if we know the charge weight of the explosives, we know where it is, we know where the geophone is, we know the whole timing sequence, and we've measured the vibration levels. For example, and also let's say we need to know the orientation of the geophone, the principal geophone pointing towards the blast. Then we can fit the model and we can start to do real practical engineering in order to get our designed outcome. However, there are a few complications easily resolved. As I said before, we're talking about charge weight and distance and vibration, but what charge weight should we use? Okay, what should we use? The total weight of the explosive charge? No, because we're going to be overestimating the charge weight that contributes. Should we use the minimum charge that's located in a single blast hole? No, tampoco, because we'll have exactly the opposite effect. Maybe it's the average charge of all the blast holes. Maybe, but that has to be examined. And if the holes are delayed by only a short period of time, and let me just show you the next piece of information here, then clearly, and I'll explain this very quickly, the total kilos contributing to a vibration intensity may not be just the number of kilos in one hole. Many of you, all of you, will have seen something like this before. Let's say we have a pulse, which is a standard pulse, and here's another version of the standard pulse. And here we've added another pulse, meaning another identical charge, but detonating, in this particular case, I think it's 100 milliseconds later. A new compound waveform looks like this, and the vibration level, the total vibration level, has not increased. But if we did exactly the same thing, but with a small delay between each successive detonation, we now produce a vibration waveform, which is more complex, and which is actually 20% higher. And yet we've used the same amount of explosive in each hole. So we have to be cautious, and we have to understand that the detonation, the initiation sequence, will have a bearing on how many kilos or how many pounds we have to really take into account with our modeling. Okay, calculating what that number should be, this number of going from 100, this was 17, by the way, clearly 17 milliseconds is not enough separation to avoid coupling. Okay, but 100 certainly is, but 100 is too much. So maybe we have to look at doing this sort of exercise to determine what that vibration coupling window is going to be. With respect to the distance again, we have to work out which distance we're going to use. Are we going to use the closest hole? People might think, yeah, because it's the closest hole, it's going to have the biggest vibration. But the closest hole might be a buffer hole with maybe three meters or 2 meters or 1 meter of charge. So it definitely won't produce the highest vibration. One option, which is often talked about these days, is to use the charge, the hole, which has the largest value of scale distance. Well, sorry, the most critical value of scale distance. The largest impact for scale distance will be the smallest value of scale distance, and that can be calculated for every single hole. We could then potentially use that hole for our charge weight and also our charge distance. That's an alternative. We're going to very quickly go through a simple example. Let's look at a 12-meter bench in very hard rock. And that very hard rock explains why we have a 406 millimeter diameter blast hole. We've got a pattern of about 9 meters by 9 meters, and we have 3.6 meters of stemming, which I pointed out is probably very questionable, probably not enough. And it's a small blast. It's a synthetic blast, 5 rows of 30 holes per blast. And in this case, there's no electronics. We're going to shoot with 17 milliseconds between rows, 42 milliseconds, within the row and 42 between rows. And we'll use a simple echelon firing that looks like this. In other words, there's a drill pattern, here's a charge pattern, and here is a pattern initiating from a corner, blasting to 2 free faces. So that's what it's going to look like in general terms. This is where it gets interesting. We'd like to know what mass of explosive should we use to calibrate our model. This approach tells us, or does an analysis of how many charges are going off in the same window of time. This is what's used to calculate the famous MIC, maximum instantaneous charge, which is often used as a parameter to design safe blasting. And the classic one is 8 milliseconds. There's a lot of work being done to publish and show that that really is completely irrelevant. We could do this, and we could then say that this amount of weight is actually what's contributing to the vibration. Now, these holes are actually not beside each other. So our distance, again, is another thing that we have to look into. But certainly, the predicted value of vibration or the predicted connection will be maybe better, but not yet precise. One of the problems is that this analysis tells us how many charges went off together in a certain time level at the blast. But we're interested in how they arrive at the point of measurement. And if they leave from different points, they may not arrive at the same time. You know, you could have 4 planes taking off from 4 different airports and still arrive at one airport at exactly the same time. That's the best analogy I can think of to describe that. Okay, so with our model, we can know in 3D exactly where the geophone is. Let's assume we have a value for the P-wave velocity or the ground velocity, and we know the delay sequence here. That allows us to predict, excuse me, how many charges are contributing, who are joining together to produce a vibration level at this point. And this is basically the last slide discussing this model. It's a simple model. It's and I won't go into any more detail, but what it does allow us to do is take into account rock properties like the P-wave velocity. It allows us to look at a number of holes detonating in a window which we specify. It might be, certainly won't be 8 milliseconds, it might be 50, it might be 100, we don't know. But we have our vibration attenuation parameters here as well. So we have an opportunity there to determine what is a good option. At this point in time, we are very close to be able to do a good engineering process to predict an outcome. So I'm confident that with this limited modeling, but high quality data, we have the ability to do quite a good job at controlling where we're going. I think we have a much better chance of staying in compliance with this kind of approach. I want to talk about, just quickly or briefly, another number of ways that we can, or number of reasons why we would engineer a different result in vibration levels. And because some of these outcomes we're looking for are not as simple as compliance, we need to look at a couple of different relationships which have to do with the mathematics of the wave propagation. And starting over here, this is our classic, what would you call it, default equation for PPV, for the particle velocity. And it's a sinusoidal function based on the frequency. And obviously, a typical blast design will contain multiple frequencies, each of those producing a waveform, which add together to give us the waveform we see when we measure with a geophone. What I want to discuss here quickly is that we can take a signal like this. We can take a signal from an Instantel or a NOMIS or any number of other vibration measuring devices, and we can mathematically convert it into displacement, dynamic displacement, by integrating this. When we integrate this, we will end up with a term involving frequency on the bottom of the equation. All I want you to understand there is that a bigger frequency, a higher frequency, is going to give us a lower value of vibration, displacement. But more importantly, if we have a low frequency, let's say 5 hertz or something of that order, it's going to give us, for the same PPV, we're going to get a much higher value of PPD, peak particle displacement. Why that's important, I'll come to very shortly. On the other side, And this is a very theoretical but valuable approach to determining how much vibration can we really feed into or subject a rock mass to. How much can we hit, let's say, the final bench wall or the bench face with vibration before we start to cause issues? And this is simply a modification, an adaptation of the law of elasticity. What we're saying is that if we divide the peak particle velocity, the vibration, by the P wave velocity, it's going to be very close or very similar to dividing the stress level by the Young's modulus to deliver the expression for deformation. We can relate this so that we have we can calculate a value of vibration which can be related through deformation to these parameters, which we can readily measure. So talking to the geomechanics people, we can know the compressor strength, the P wave velocity we can measure, we can know the modulus, so we can actually calculate a value of vibration. And truly, this is vibration 101, I know. But we can calculate a value which is related to the amount of damage we're going to be doing to the rock. So we have another reason now to calculate the vibration, to predict the vibration based on engineering the design. I'm going to go into almost no detail with these slides. All of this, sorry, I should point out one thing that we discussed with the people from the university and with John is the importance of sharing. So this presentation in PDF will be available through the ISEE chapter. Should anybody wish to review it, with more calmness. It also means that I don't have to go into detail with every single one of these boxes. But basically what you'll find here is listed between this slide and the following slide, which is that one, a series of phenomena or results which result from the raw vibration that we're pumping into the rock. So we have, and again, green and red. Fragmentation is a good thing, damage is a bad thing, microfracturing is a good thing. I'll dwell just quickly on this, where when I say near to midfield, I'm talking about damage which doesn't depend exclusively on vibration. It might be something as simple as reaction forces from the lack of ability to displace a muck pile. And again, and for another day, we can talk about damage from that source. Over here, the one that I do want to talk about is this thing about destabilizing the large structures. You remember I talked about the fact that low frequencies of vibration, which is the hertz, will produce higher values of PPD, and that has a tendency to destroy the cohesion and friction angle in structures which up until that point were quasi-stable. They were cinematically stable. Mess with this and all of a sudden all bets are off and we could have a structure rolling down the hill. So, and again, this comes back to what this means is that we have the ability to cause problems, but we also have the ability to avoid those problems. And that's the thing to stress in this, this particular subject. We can engineer out risk. And that's the whole reason that we do what we do. Issues like annoyance, structural damage, and so on. I'm talking here about far field outside of our mine lease. Again, vibration is an issue, but air overpressure is an issue as well. So we're talking about decibels, and obviously we're talking about linear decibels. I've seen operations where the microphone never gets plugged in, and that means that we may be causing more damage than we expected to cause. When you create a vibration wave in the air, it travels obviously freely until it hits, let's say, a diaphragm, like, for example, a drum skin. Imagine that as the air blast hits a large planar structure, it will cause that structure to vibrate. A good example of those structures is a glass window, or perhaps the sheet metal side of a truck shop, or a garage, or a workshop. In other words, this vibration travels through the air and then hits the structure. So air blast is a big problem, can be a big problem. And again, you have to be careful about that. Also, the hertz here, I refer to the possibility of avoiding resonance in some of these structures. Okay, so that is a relevant thing. Down the right-hand side, I don't have time to go into these details, but we talk about the different aspects of the design which we can work with to reduce these impacts and therefore reduce these problems. Okay, so just a couple of quick examples towards the end of the talk here. Here I'm going to talk about the engineering design for vibration-induced fragmentation. So no longer are we worried about compliance with the authorities. Now we're worried about compliance with far more important people, who are the people who control the shovels and the trucks, but even more important, the people that control the other side of our fence, which is the plant, whether it's a concentrator, whether it's a heap leach operation, whether it's just a series of crushers to deliver good road base from a quarry. All of those things, these are now our customers, these are our clients, and they have their own wishes about what they want from our fragmentation. Okay. Now, it turns out the tools that we use, which I showed you before about calculating how superposition of waves can produce a higher intensity vibration wave based on the timing of the blast. The same thing actually works in the near field. In fact, in some senses, it actually works better in the near field, as I'll show shortly. And again, this is something which can lead into quite nicely complicated modeling, which will probably crop up in the session next week. So again, beginning with this simple waveform superposition and gradually increasing, let's say, the complexity and the power of our analysis algorithms and models, we can actually start to take into account the rock mass in a lot more detail. We can actually begin to do explosive energy engineering. In other words, we can change the amount of vibration we deliver by choosing more powerful explosives or less powerful explosives, higher VOD explosives or lower VOD explosives. We have a range of things that we can do just by playing with the explosives. Sorry, please don't play with explosives, very unsafe, but just by making adjustments to the explosives that we use. And also, as I said before, flexible timing control. This is our fine tuning. This is our coarse adjustment. This is our fine adjustment. Okay. So as I said before, here are our waveforms, and we can do things like this. We can actually run a whole series of simulations of adding these two waves together at different timing to establish the effective timing on the summation, the actual peak vibration as calculated by adding these two waves together. The original wave was around about 0.5 millimeters per second, and we can see that we can get to 0.8 or even higher simply by messing with the timing. Okay, and that can also be related to the fragmentation index. The fragmentation index is simply an index which is an estimate of how much of our vibration is going to exceed a level which we believe will give us good fragmentation. That comes back to the previously calculated value of the maximum peak particle velocity that we looked at just previously a little while ago. Again, another outcome that we're engineering for. What do we have available in the industry and in the literature? This is one example which comes from work done by Claude Cunningham, quite a famous researcher and worker in the field. And what Claude came up with was this actually some adjustment of previously done work. Well, what he's looking at is the effect of the interhole or intercharge delay, measured in this case in milliseconds per meter of burden. Keep that in mind. He's looking at how these changes affect D50 or the D50 multiplier. In other words, if I start with a fragment that's 10 millimeters or 10 centimeters, this is going to be a multiplying factor to apply to D50, the 50%. So I can actually come up with timing combinations which will minimize the amount of or actually maximize the fragmentation, sorry. And in this particular case, Claude came up with a very simple equation which can be at least used to have a look at getting close. Now, from the previous slide, this graph here is interesting, because what it's saying, sorry, the other one, is what happens here where our delays start to get below 10 milliseconds, in this case, between charges, okay? At this point, the relationship can get very interesting, which is probably the most complex thing to talk about here, and also close to the end. On the left here, we see a very similar graph, and this graph was produced by a number of experiments by some very clever investigators, people like Takis Katsabanis, Eamon, and I will always mispronounce his name, but Tewodros, a gentleman who works for one of the explosive companies. But they did a lot of large laboratory work, which came up with the same kind of curve. What's interesting here is that there seem to be two schools of thought. One school of thought says, if you use this kind of delay scheme, you'll get the best fragmentation. On the other hand, there is another school of thought, and Cameron Mackenzie, who a lot of you would know very well, talks about the Chilean paradigm, the Chilean timing concept, which is all about blasting primarily for comminution, for crushers, and above all for SAG mills. And you can see there that uses much, much quicker timing. In fact, this timing has been used in Australia, and they call it Latin American timing, or LAT timing, which just goes to show the influence that we Latins, quote unquote, can have on the rest of the world. So that's interesting. We have two schools of thought about this. Now, the resolution of that doubt, or that contradiction, let's say, comes by, or can be solved by looking at this other graph here, which is also looking at delay times, but now we're not measuring fragmentation. We're actually measuring point load index. In other words, we're now measuring how hard rock samples are after blasting using different delay design criteria. So, and you'll see it's very interesting. Above a certain timing, you'll see that the delay actually has no effect on the point load index. But as we go closer to, well, closer to zero, and obviously, you know, very close to zero, we see that we can actually decrease in here the point load index. What that means, without going into too much detail, is that we've made the rock softer simply by virtue of the timing. Now, there are other concepts, there are other issues with that very quick timing. You have to also make sure that the geomechanical engineers are not too concerned about causing vibration damage. This will produce more vibration, and this vibration will have an impact which is most interesting, which is to increase the number or the amount of micro fracturing, micro cracking inside each fragment. It is absolutely possible to have a distribution of fragment size, which looks like down here, but each of those fragments has been conditioned to basically behave like a softer rock when it gets to things like the crusher, primary crusher, secondary crusher, SAG mill, ball mill. So we've actually made all of our downstream comminution properties much more suitable for our circuit, again, through a process of engineering design, which fundamentally relates to the vibration that we produce by being clever at the design stage. And I think the last technical slide is essentially this one, where what I'm showing, sorry, the last image. And this is a very simple image, which again was calculated and created by Cameron Mackenzie for a paper that I was lucky enough to be involved with him. And this shows essentially the distribution of energy intensity, vibration intensity, depending on the timing. 9 milliseconds between charges, 5 milliseconds, 3 milliseconds, and here 1 millisecond. So from a damage point of view, this could be a nightmare. But if it's far away from the final wall, it could well be that we're producing lots of really cool microfractures and making the life of our plant brothers a lot easier. This is the last slide. And again, I will go through this very quickly. We're almost out of time, and I wanted to leave time for questions, so my apologies. But anyway, the requirements. What do we need to do this engineering process well? In a perfect world, we want detailed knowledge of the engineering materials that we're working with. And that means the rock mass, of course, but also the properties of the other materials we use, like the explosives and the accessories, the delays and what have you. The stemming is also another engineering material which we need badly. We need to understand the limitations and the operational effectiveness of some of the tools. Powder factor is a tool, but we know, all of us, that increasing the powder factor infinitely is not going to give us improvements infinitely in our process. So we have to be clear on what can practically be achieved. You can engineer anything on paper, but it may not be possible. We have to know where our ambition needs to stop. So we also need a clearly understood but functional, flexible model of vibration to explain the relationship between the things we do, how we execute that design, and what outputs do we produce. Okay, so we need a causal model. It must be coherent, and we have to describe a chain of actions and reactions or consequences from the detonation all the way through to breakage. Sorry, there we go. And we also have to obviously have a rich and hopefully large database of measurements which have been carried out with a lot of rigor and using the best possible technology. As I've said here, technology available to confirm or refute the models. In other words, high-level measurement capability. High-level analysis, we need to be as clever as possible and as detailed as possible with that analysis, which will then give us a much better possibility of having high-grade models. Okay, and this one is the last one. It's soft science, if you like, but we need to have the ability to have clear and unambiguous communication to explain what we're doing and to convince the people above us who are more concerned, and hopefully I don't offend anybody, but more concerned with budgets, staying on budget, reducing costs and what have you, who may need to understand that you can spend more money and you can make a lot more money. So I guess what I'm talking about here is I said a new engineering discipline, but what I really mean is a more widely accepted engineering discipline. And again, what I'm talking about there is a test or a trial or a project can be authorized and it can be observed, and it's usually a lot of fun and it's evaluated, and quite often it's found to be successful. Mine-to-mill projects, they are a classic example of this. But a project is like a nice party. At the end of the day, the party's over and we go back to doing what we did. For mine-to-mill or mine-to-leach or mine-to-fines, whatever, it has to become a discipline. It has to become an engineering discipline, not just a project. Okay, and this can mean more expenditure, more cost, but again, we are very confident that that means more revenue. Okay, and that requires very effective communication to the people who control the extent to which we can carry out the engineering that we are so enthusiastically looking to develop. That concludes the technical part. Just before I finish completely, I just wanted to make some quick acknowledgements. The first one is to the fact that this presentation includes images and figures from previous published work, which was done by Cameron McKenzie from Blast Technology, Austin Powder. I was involved with both of those groups, so hence my access to that information. The imagery from that analysis of vibration was carried out using a very simple software, which I don't actually think is available anymore, called Blast Plan. But this same sort of analysis can now be done on pretty much all of the classical blast analysis and modeling software packages. Again, very much like to thank the board of the student chapter of the ISEE from the, I'll say La Cato, if that's allowed. And very much appreciate the invitation to be with you tonight and to I guess, communicate some of these ideas. And a last word, I'd like to acknowledge and say thank you for the support and the encouragement of John Watson, who's here. John is an ISEE guru, and as anybody from Australia will know, this is high praise. He's a general good bloke. So again, thanks, John. And that is it. So basically, thank you again. This has been part 1, and don't miss part 2. So again, apologies for running over time. I hope it was worthwhile. And if there's any time left, I'll be more than happy to answer questions, or at least try to answer questions. So again, thanks very much.
Thank you very much, Bill, for your presentation. It was really, really good. And on behalf of ISEE PUCP chapter, we are really glad you gave your presentation. So now we have the questions on, and we have many questions. And also, we are also in this webinar to be worldwide, and despitefully, many of us, of the attendees are in Asia or Africa, and the time zone is not good. So many of them can't come because it's like 3 a.m. in Africa or Asia. So now I begin with the questions on, and yeah, we have really good questions. And Bill, can you hear me? And yep, can you hear me?
I can hear you. I had my microphone turned off just for a second. That's all.
Okay. Yeah, I will live with my fluency in English. So
your English is very good.
Thank you very much. And the first one is from Sergio Tamay from Brazil. The double initiation, two electronics deaths on top and bottom with same time involved can affect the vibration comparing with single initiation. And also I will send you by the chat so you can see this. And yep, this is the first question from Brazil.
Okay. Well, firstly, that's an excellent question, and it's a question which we've been asking from even before that we had electronic DLAs. This concept of simultaneous initiation of a charge in a hole has been discussed for a long time. Really, it wasn't until electronic initiation was available that we could actually do it, because the scatter, as you know, the scatter in delays would essentially maybe prevent there being two detonation fronts colliding in the middle. I like very much the idea. It appeals to my simple visual approach to engineering. I've actually been discussing this subject a lot recently with one of the major explosive suppliers here in Chile, where they do use this technique. As I said, I think that for me, it makes sense. I've done simple modeling, and I've worked with other people who have done simple, well, not that simple, and actually dynamic close-in C wave modeling. And maybe Stuart will talk about this next week. But if not, I'm sure we can talk again. I guess the real issue is whether or not you can actually see the results. And this is my doubt. I've never actually had the opportunity to examine the fragmentation very closely from a blast where this is being done. In the very near future, I'm working with a client who is going to do that. So we will be doing tests with that simultaneous initiation, and we will have a very good fragmentation assessment system. So maybe within a few months, we might have results that can be published. I do have a good friend in the States who has done a lot of this work, doesn't disagree with the concept, but hasn't been able to find the results that we're looking for. So I guess the answer is a bit more complex. I like the idea, it makes sense to me, but so far I've not been able to see it as a result. But I haven't given up. I think that, and a lot of people are still trying to collect that good data, which will allow us to see finally if it is a valid process. So I'm sure that doesn't answer the question completely, but it's the best I can do at the moment.
Thank you very much, Bill.
Well, if that's it, thank you for playing. Do you have more questions?
Sorry, Bill, I have a problem with my macro. I can. So now I'm here. We have the second question. It's from Nancy Vargas and from our university. So, in your experience, which is the reliability of the model? And in your opinion, are there other variables that should be considered in the model, but maybe are too hard to measure, so are left out of the model? So I'm also sending the question in your chat, Bill.
I can't see that chat. That's probably because I'm not very
Okay.
good at.
Okay.
Hang on. Sorry. Yes, I can see that chat. There it is.
Okay.
Okay. That again is a really good fundamental question, and the short answer is a very famous answer. It's garbage in, garbage out. In other words, the more the higher the quality of the information that you put in, data, the more reliable that model will be. No model is perfect, and certainly the scale distance model is a good beginning. Is my mic on? Sorry. Yes, it is good. But there are other subtleties which we need to think about, and I didn't have the chance to go into these. Something else we need to keep in mind is that the geology is not isotropic. So if we have, let's use the first example of compliance. If there are 3 different places that we have to comply with our vibration, let's say that there's a church, there's a school, and there's a house of a very successful lawyer, and they're in different places. So now we have to come up with a blast design which allows us to control the vibration in those 3 places. Obviously, the place we're going to be most concerned about is going to be the house of the lawyer, but we're also concerned about the other 2 places as well. And the issue there is that the geology between our blast and those 3 places could well be very different. So that means that we can try and use the same model, but we have to calibrate it for every circumstance, every different set of geology. There are other models which are much more sophisticated. And again, this is not the time to go into them. But again, we have to focus on good data. So I would begin using the model. I would focus on the amount of quality in my data, and I would then look to expand my analysis into other more complex models. Okay. And again, I don't want to get too far into that because I know that that Stuart Brashear will be talking about some of these models next week. So tune in next week.
Great. And we have from Paulo Leon from Dominican Republic, República Dominicana. Could you please give to us your advice to set up the monitoring station? Means the best design. A station must be mandatory set up over rock, or it can be over the soil profile. I'm also sending the question to your chat, Bill.
Sure. Again, that's a very good question. The geophone is going to measure whatever vibration comes to it. And within certain limits about vibration amplitude and vibration frequency, it will measure what it receives. Now, what we have to keep in mind is what is the behavior that we wish to measure faithfully. Okay, so if we're concerned, as we should be, about the vibration traveling through the rock, then the geophone or the accelerometer has to be in close contact with that rock. And there are a number of ways to achieve that coupling. Some of them are more difficult than others. The classic one, which was used a lot when I was once upon a time with the JKMRC, is to drill a hole in the bench, for example, behind a blast, or drill a shallow hole on a bench which is 500 meters away, and put a geophone, a triaxial geophone, into the ground, fill that hole full of cement, And that is maybe one of the best ways to put a geophone into the ground. Of course, that geophone is lost, but I would rather say that geophone is invested. When we are further away, a valid technique which doesn't allow or doesn't cause us to lose the vibration, the geophone, is to maybe excavate a small hole, fill that with cement, clear or clean or smoothen the surface, bolt some sort of aluminium plate, if you like, onto that, and then you can screw the geophone puck or geophone sonde onto that piece of rock. I say aluminium, maybe it's no longer a concern, but back in the day, the crude geophones used to not have very good protection from magnetism, and they rely on magnetic reactions. So if you put a geophone in very close contact with iron or steel, you may well be distorting its response. The question of mandatory is a difficult one. As I said at the beginning, the ISEE has a very good standard or guide, and I would encourage anybody to get in touch with John, with John Watson, who is probably our expert, or even actually Stuart Brashear, who have a lot of knowledge about this particular field in terms of, what are the recommendations. Things get underground, it can get even more difficult, I should point out. So I hope that helps up there in the DR. La República Dominicana.
República Dominicana. So this is the last one. That was the last question. And also, Bill, we are going to have the probation of this, and this will be shared in our YouTube channel, and also greetings to the people who will see in another part of the world because it's the time zone. So now we will begin with the end of the webinar. Also, yeah, we are really glad that you have attended this webinar, and also thank you, John. Nancy, you can begin with the end of the webinar. Nancy.
Hi guys. Well, now that the Q&A sections are, good night to you all. My name is Nancy. Thank you all for having joined us today. Hope you're having a great week, and well, to my Peruvian folks, I know the results on Sunday weren't pleasing, but we gotta keep on going. This was last design pattern for vibration control part 1. We wanna give a special thanks to Mr. Adamson for such an amazing webinar. Thank you so much for your willingness and your predisposition of sharing some of your knowledge with us. Also, we want to thank Mr. Watson for supporting us during this process. He was kind enough to offer his help to our chapter, and without him, let's be honest, any of this would have been possible. So please, Mr. Adamson, could you stop sharing your screen so that we can promote the next webinar?
Did that work?
Yeah. No,
okay.
Please, good. Yeah. So next slide, please. No. Before ending this webinar, no, please, next slide. Yeah. Before ending this webinar, we wanted to invite you guys to the part 2 of this webinar series. It will be next Wednesday at 3 p.m. Eastern Time. It will be in charge of Mr. Stuart Brashear and Mr. Andrew Craig Johnson. Additionally, we'll be fortunate enough to have Mr. Adamson join us this day, that day. We'll be sending the invitation to your emails, and we'll be posting also the flyer and the link inscription on our Facebook and LinkedIn page. In the next few days, I think that by Friday, it should be there. Well, here in the ISEE PUCP student chapter, we have this tradition to shout fire in the hole at the end of each event, each webinar. So please turn your mics on, and on the count of 3, everyone will shout fire in the hole. Please. And no, you could stop sharing. Please turn your mics, your cameras on, so that we can shout fire in the hole.
Enciendan sus cámaras y también
Don't be
tenemos en la
shy, guys.
comunidad latina. Hay de Chile, hay de toda Sudamérica, así que invitamos a que los enciendan porque estamos creando una serie de webinars y ya, bueno, son parte de la comunidad ISEE PUCP. So I encourage you to turn on your camera. And yeah, we are creating this ISEE ISEE PUC series. We are creating a community. So please turn on your cameras to notch each other. We're really glad. Nancy, you can.
Yeah. Well, I will start counting then. Even if you don't turn on your camera, you could show it anyway. So there's no problem. Well, 1, please everyone, get ready. 1, 2, 3. Fire in the hole.
Fire in the hole.
In the hole.
Oh,
Amazing.
Keep your powder dry.
yeah.
Tap or light.
Yeah.
Tap a light.
Thank you again, everyone.
Guys, you did a great job, guys. Appreciate the help, Bill.
Oh,
Thank
a
you.
pleasure, man. A pleasure. And sincere congratulations to all the next generation there at the university. Done a fantastic job.
Well done, Bill. Good
Thanks,
hearing
Betty.
from you.
Yeah.
Good job. Congratulations from Spain.
Muchísimas gracias.
Thank you so much. Thank you again for joining us and hope to see you next week. Take care and keep safe.
Thank you so much, regards from Bolivia. Thank you.
Chao, chao. Que estén muy bien. Cuídense todos.
Thank you for
Take care. See you next week.
Thank you.
See you next week. And well,
See you next week.
this is the end of the webinar. And thank you very much for attending the webinar. And well, muchas gracias a todos por atender este webinar. Y ya nos estaremos viendo la siguiente semana. Hasta luego. Chao.
Luego, chao, chao. Gracias,
Bye, bye.
que estés muy bien.
Nos vemos.